The next goal is goals 6 and 7. You're going to state and describe the law of conservation of momentum. So when we look at this example, we have object A and object B. So those are the two objects in this situation, A and B. The system would be the whole combination of the whole thing. So the system is A, B, and the spring in between them. So according to the law of conservation of momentum, what happens to the momentum of the system? So the law of conservation of momentum, what that means is the entire system, the momentum before the explosion, in this case, the spring will push the two boxes outward. The momentum before the explosion is going to be equal to the momentum after the explosion. So the momentum of objects A and B will change when the spring is released, but why won't the momentum of the system change? So if we look just at A, if we only examine A, the momentum before, which is really P, right? The momentum before is going to be 0 because it's just sitting there. And we agree that if we look at just object A, the momentum after, okay, so this is for object B, this is before. If we look at the momentum after, then it's going to be moving, right? Because it's M times V. After it's moving, it's going to have some value of momentum. So if we just look at A doesn't change its momentum, or A does change its momentum. And B would be the same case. It's going to feel a net force, the B is going to start moving. It will also have a momentum. So each of them individually experience a change in momentum. But when you add them together, since they're going in opposite directions, they're going to cancel out and you're going to have 0 momentum. So if you did a little bit of a math, you could have, let's say, box A has a mass of 1 kilogram and B has a mass of 2 kilograms. All right? So before the explosion, the momentum before is 0. Okay? But after, we'd have to add up the momentums of each one. Momentum of A plus the momentum of B, which is M times V. So if this is 1, let's say it's going at 10, but it's going to be going to the left, so we'll make it negative 10. Plus the other guy is 2, but since it's bigger, it's not going to be going as fast. So let's say it's going to be going 5. So 1 times negative 10 is negative 10, plus a positive 10 equals 0. So that's why you can have the individual guys gaining momentum, but when we look at the system, they will cancel out and be 0. For goal 7, you're supposed to use the law of conservation of momentum to determine the final velocity on the system after a collision. All right, and so I'm going to put these equations up here. If you like using them, we have them available. All right, and we're going to look at the scenario and decide which one works out best. So if we look at this first example, this girl is standing there. Somebody throws her, actually it's a basketball in the picture. I use backpack in there, but same idea. So basically, what's her mass? Before, her mass is 40 kilograms. And she's standing on an unmoving, actually I should have changed this to roller skates, but her velocity is just standing there, so it's 0. Somebody throws her a 10 kilogram object, and the velocity, they tell us, is 4. Oops, I wrote 40, get rid of that. So 4 meters per second. So what I can do is I can calculate the momentum of her and the ball before she catches it. So to do that, I'm just going to take M times V. I'm going to add M times V for the second object. So this would be 10 times 4 plus 40 times 0. So if I finish this off, this is 40 plus 0. So what I really have is 40 equals whatever happens in the after. Oops, you can't see that. There we go. So now, if we take a look at the after scenario, we have to consider the fact that both the girl and the ball are connected together, and they're going to be traveling backwards with the same velocity. So we're going to use the equation that is velocity final times m1 plus m2. So she is connected. So we're going to take the mass of the ball, and we're going to add it to her mass, and we're going to look for our unknown speed. So VF times 50, and I'm going to write that down here, VF times 50 equals 40. So to solve for VF, I divide both sides by 50. So 40 divided by 50 is what, 0.9? 40 divided by 50 equals 0.8. So we got VF equals 0.8 meters per second. And the second problem is going to be a collision problem. So we've got a bowling ball, and we know the mass of the bowling ball is 7.5 kilograms when we read the problem. It's moving down the bowling alley at a speed of 9 meters per second, and it hits a bowling pin whose mass is 2.5 kilograms. As you know, when you're bowling, the pins at the end start at rest. They're just sitting there at the bottom of at the end of the alley. So we're going to take our mass of each one, and we're going to multiply them together and with the velocity, and we're going to come up with the momentum of both of them before the collision. So we're going to take 7.5 times 9, plus, this is easy because 2.5 times 0 cancels out. So 7.5 times 9 ends up being 67.5 plus 0, so that equals 67.5. Now, that's going to equal the momentum after. So notice, when you bowl, right, the bowling ball doesn't hit the pin and stick together. They are moving off in separate directions. So what's really going on here is we've got a mass, and that bowling ball mass will have its own velocity, and the second mass, the pin, will have its own velocity. So we're going to use the equation with this ending. So what I'm going to do is just plug in, my masses don't change, so my mass of the bowling ball is 7.5. The mass of the pin is 2.5. So I know that they tell us that after the collision, the pin flies away with a velocity of 11. So I have to be careful and put that velocity with the pin, and not with the bowling ball. Because they're asking me, what's the velocity of the bowling ball? So this guy is my unknown velocity. So I'm going to simplify on the right as much as I can. So I'm going to take 2.5 times 11, and that turns out to be 27.5 plus 7.5 V1. So I'm going to write that down here so I can have it closer, plus 27.5. So now I have to solve for V1, and I can't. I have to subtract 27.5 first. So 27.5, so that's, I should be able to do that in my head, but 67.5 minus 27.5 turns out to be 40. So I have 40 equals, this is gone, 7.5 V1. So then I'm going to take my 40 and divide by 7.5 to end up with 5.3. Divide both sides by 7.5, so V1 equals 5.3 meters per second. And that would be how you do these two problems. So I'm not going to worry too much about these. I don't get into them on the test, but that would be how you solve those problems.